Hi, welcome back to Programming in Python Learning Series. This is session 13. In the previous sessions, we saw topics till queues, and in this session, we look at sorting. So, what is sorting and why do we need sorting, right? Sorting is nothing but arranging a collection of elements or data elements in a particular order. Collection of numbers can be sorted in ascending or descending format, and collection of strings can be sorted alphabetically, A to Z or Z to A, or by length of the string. And there can be other sorting orders also. It depends on what we want to use. So why do we need sorting? When we have to deal with a huge set of unordered data elements, and we need a particular order to kind of process data in a particular format, or we want to quickly identify certain specific data element, sorting really helps. Without sorted data, it will be very difficult to find out if it is present itself or not. So it avoids chaos in certain situations. So what are the types of sorting? First one is a bubble sort. Bubble sort sorts a list of elements by repeatedly comparing adjacent elements. Take one, compare with the second one, and second to third, and so on, and swaps their positions if they are not ordered already. It compares, for example, it compares element 1 and 2, and we are looking for ascending or descending order. If they are not in that order, swap the position. Otherwise, just keep them as is and move on to the next element. So it's basically bringing one element before or after other based on the order we want. The order can be ascending or descending, and n minus 1 passes are made to sort the elements, where n is the total number of elements. Second is the selection sort. Sorts the list of elements by traversing the unsorted list, finding the smallest element in the list, and swapping that element with the leftmost element of the list. Move through elements left to right, find the smallest in that particular pass, and place it at the leftmost of the list, meaning first of the list. In the next one, the previous smallest element at the leftmost position is ignored, and the rest are checked for the smallest again, and so on. So, identify the smallest in a single pass, place it at the beginning of the list, and in the next pass, ignore that, just check the rest for the smallest and place it next to that. Not the leftmost again, but place it before the previously identified smallest element, and so on, until every element is kind of placed in the order. Third is insertions. Each element in the unsorted list is considered one by one and is inserted in the sorted list in its appropriate position. In each pass, the sorted list is traversed from the backward direction to find the position where the unsorted element could be inserted. Meaning, I identify elements and put it in an order, kind of a sorted list, and then in the sorted order, if I'm coming across an element, where to place it? Should I place it before all the elements, or middle of the elements, or at the end of the sequence, and so on? So it's basically placing the new element or newly processed element into a sorted list in an appropriate position. We'll talk about bubble sort first. In each pass, the required pairs of adjacent elements of the list will be compared. To arrange elements in the ascending order, the largest element is identified after each pass and placed to the correct position in the list. It's meaning bubbling up. I mean, smaller to largest, I'm going to stack them, having the largest element coming up to the top. This starter element is not considered in the remaining passes, and thus the list of elements get reduced in successive passes. This is an example. See, in the pass one, when I have elements 6, 4, minus 5, and 9. In the first pass, since 4 and 6 are not in the order, 6 is supposed to be larger than 4, so I'm having a swap here. So 4 comes first and 6 later. And then there is another comparison, another swap happening again, because 6 is larger than minus 5. And when 6 and 9 are encountered, since they are already in the sorted order, there is no change. So this is the first pass. So here, one element is compared with the previous one only once, and the comparison moves to the next set. So whatever happened, or whatever element that is undisturbed from the first pass just stays there. For example, in the last row, we have 4, minus 5, 6, and 9. There is no going back to 4 again, because 4 is moved, and the comparison moved on to the next set of elements. In pass 2, these two are addressed, 4 and minus 5. So 4 comes after minus 5, after the change, after the swap, and then the rest of them are in order already, so there is no further change. So the final sort is minus 5, 4, 6, and 9. However, we have to remember it will take n minus 1 passes, where n being the number of elements in the list, right? So I've just given pass 1 and pass 2, but there will be a pass 3 where nothing happens. And the same minus 5, 4, 6, and 9 sequence will be repeated as they are. However, there will be a pass 3 because it has to go through n minus 1 passes. So here is the algorithm for implementing bubble sort. Define the function bubble sort with list and the number of elements in the list as parameters. Step 1, set the counter I equal to 0 for the passes. While I is less than the number of elements in the list, repeat steps 3 to 8. It's not less than or equal to, less than, which means n minus 1 passes. Set j equal to 0. This is to deal with the number of elements across each pass. While j is less than n minus I minus 1, repeat steps 5 to 7. This is to run statements in steps 5 to 7 for each n minus ith element. If the element j of list is greater than element j plus 1 in the list, then swap them, meaning the element on the left is greater than the element on the right in the traverse process. Swap them and bring them to ascending order, and set the j value to be j plus 1. Since we have swapped, we have to move to the right or move forward. So set the value to be j plus 1 to deal with the next set of elements for comparison, and set I to be I plus 1. Let's look at a program that has an implementation for bubble sort in ideally. Here is the program to implement bubble sort. As per the algorithm, I'm defining a function bubble sort with a list and finding the length of the list. Of course, I'll be giving the list values while calling the function, but to find the length of the list and print the list size just for reference, and print the list itself. For I in range n, remember range function takes from 0 to n minus 1, so I in range n will go up to n minus 1. For I in range, for j in range of 0 comma n minus I minus 1. This is as per the algorithm because the last I elements are already sorted. So I'm going to have j in range 0 to n minus I minus 1. If the list element j is greater than list element j plus 1, swap them. Swapping is basically positioning the elements in the list straightforward. Make j to j plus 1 and j plus 1 to j, and print that list for reference. Now, before calling this bubble sort, I'm giving the list. This can be received from the user with some coding. Here it's hard coded. Call the bubble sort function and print the sorted numbers. Let's run it and see how it works. This is the output of the program. Since I've asked for the list size and the actual list itself is to be printed, first two rows, I'm getting those. The first iteration or first pass, 7 and 7 are compared. they are same, so they are placed as is. 7 and 12 are compared. 12 is larger, 7 is smaller, they are in order already, so no change. 12 and 2 are compared. 2 is smaller, 12 is larger, so 2 is placed before, 12 later. 12 and minus 7 are compared. Minus 7 happens to be smaller, so that is placed before 12. 12 and 3 are compared. That is also smaller, so 3 is placed and 12 at the end. So after first pass, this is how the list looks like. Now in the second pass, 7 and 7, no change, so they are placed as there. And when 7 and 2 are compared, 7 happens to be larger than 2, so 2 comes here, and 7 is compared against minus 7, which is larger than minus 7, so minus 7 comes or is placed before 7. 7 and 3 are compared and they are swapped. 3 is placed before 7. When 7 and 12 are compared, they are in order already, so they are placed or positioned as they are. So you see how the iterations are happening or passes are happening, right? So in one pass, the entire list is traversed through. So likewise, we have treated and the finally the sorted list is getting printed. Remember we talked about n minus 1 passes happening for n elements in a list, right? So these two are anyway from print statements before the start starts, and these 5 are the actual iterations or passes, and this is the final one, end of iteration, right? So we have 5 passes happening. Just notice that by fourth iteration itself or fourth pass itself, things came to order. So if you look at it, fourth and fifth passes have the same uh, list order, right? But since the process takes n minus 1 iterations, it has to go through, though there is no change in the order itself, it has to go through n minus 1 pass. This is one example where even if there is no sorting or actual change happening or swapping happening, the process goes through n minus 1 passes. Next is the selection sort. Here is the process. The list is considered to be divided into two, one for the unsorted and the other for sorted elements. It's not kind of physically split into two. It's kind of a virtual or from the memory part of it. So one side it's going to be building up the sorted elements or arranging the sorted elements. The other side is going to keep pushing the unsorted ones for traversing through. It sorts the list of elements by traversing the unsorted list left to right, finding the smallest element of the list, and swapping that with the leftmost element of the list in the ascending order. So here is a sample. So here we have 5 elements: 64, 25, 12, 22, and 11. This is the index 0, 1, 2, 3, 4. Index value starts from 0 going for n minus 1 in the element number. The smallest element between 64 and 11 is 11. So it basically swaps these two. It's not shifting, moving across. It just swaps the positions and places 11, which happens to be the smallest across all the elements, puts in the position of the leftmost in the order. And wherever 11 was present, it takes the leftmost element that is presently there, puts into where the smallest element was present earlier. In the second pass, remember whatever was found as the smallest element that was placed in the leftmost position will be ignored in the second pass. So in the rest of the elements, while traversing, 12 happens to be the smallest, so that will be placed in the new left position of the current list. When 11 is already there, so the new leftmost will be where 25 is present, and that will be swapped across. Now in the third pass, 22 is identified to be the smallest, so that is placed before 25, and it's kind of all set: 11, 20, 12, 22, 25, and 64. So finally, we have the ascending order of elements. Here is the algorithm to implement selection sort for ascending order. Define a function selection sort with the list and number of elements in the list. To start off, set I equal to 0 while I is less than n. Repeat steps 3 to 10. Set the minimum value to be I and set a flag for swapping. Whether the swapping happens or not, you have to monitor. So set a flag which will be toggling between 0 and 1 when swapping happens or not. Set j equal to I plus 1 while j is less than n. Repeat steps 6 to 9. If j is less than the minimum value of list, then swap. So you have the swap flag to be 1 and your j whatever is found to be smallest, bring it before or swap in the position. If flag is 1, then swap those. Set I equal to I plus 1. Let's look at a program that has the implementation of selection sort. Here's the program. As per the algorithm, define a function for selection sort. Initialize I to be 0. Find the length of the list that we are going to pass or we are passing to this function. Just have a print for reference. For I in range, number of elements. Set the flag to be 0 to start off. Then minimum value to be I. And for j in range, I plus 1 till the length of the list. If the element at j is less than the element at whatever we are traversing through, set the minimum value to be j and swap flag to be 1. Whenever the flag is set to be 1, I'm considering that particular elements need to be swapped because one of them is the smallest. If flag is 1, the element at the position index position in the list min, and I swap them across and print the list. Print the current status within the range, and we'll have a final print after all the sorting is done. So I'm going to give a list of numbers hard coded. Print whatever was given as the original list. Call the selection sort function, and then get the final sorted list. Let's run it and see what the output looks like. So here is the output of the program. This is the original list I had hard coded in the program, and the number of elements happen to be 6. And here is the traversing or each pass, and the end of each pass, how my elements of the list look like. So right after pass 2, the given numbers look like they have come to the ascending order. So the next passes, all the next passes, nothing happened as in terms of sorting or swapping, but they went through all the passes. Just another example, just happened to be another example where nothing much happened in each pass except one or first two passes, but yes, the process went through number of iterations that it actually supposed to do. The next method is the insertion sort. There is a process. Each element in the unsorted list is considered one by one and is inserted into the sorted list at its appropriate position based on whether it is smaller or larger. In each pass, the sorted list travels from backward direction to find the position where the unsorted element could be inserted. Let's look at an example. So I have numbers 23, 1, 10, 5, 2. After the first pass, it's remaining the same. And the second pass, when I'm traversing from left to right, I find that one happens to be or one should be in the first position because that is smaller. So end of the second pass, I get 1, 23, 10, 5, 2. And in the third pass, 10 is identified to be in the position between 1 and 23 because in the ascending order, 10 should be before 23. And in the fourth pass, you have 5 should be coming before 1 and 10, and the final 2 coming before 5 after 1. It's basically positioning, when taking one element at a time and see where to fit in based on the order we want. If it is descending, it will be totally the opposite. Between 23 and 1, nothing will happen. And between 1 and 10, 10 will come in between 23 and 1, and so on. So depending on the order we require, and going through each and every element, find out where should fit in, and in the order from backwards. Here is the algorithm. Create a function insertion sort with the list name and the number of elements. Set I equal to 1. While I is less than 1, repeat steps 3 to 9. Create a temp list for our temp element series for positioning of elements. Set j equal to I minus 1. While j is greater than 0 and the jth element in the list is greater than 10, repeat steps 6 to 7. Step 6 is swapping the elements at j plus 1 position with the element at position j, and set j value to be j minus 1. Now, the j plus 1 element will be set with the temp value, which is the ith value, and set I equal to I plus 1. Now let's look at a sample program that has insertion sort implementation on the IDE. Here is the program. I'm defining a function insertion sort with the list that I'll be providing. Here in this program again, the list is going to be hard coded, but there are other ways to receive the list, either from user or reading from a file and so on. But in this case, it's going to be uh, an hard coded list. Remember, any function before being called should be defined. So we are starting with the function definition, and as before, I'm getting the length or the number of elements in the list and printing that just for reference. And for I in range up to n, set the value at ith position into the variable temp, and j to be I minus 1. As long as or while j is greater than or equal to 0 and the temp is less than the value at position j, swap the elements. Meaning, as long as the value is found to be smaller or should be between two elements, keep swapping. Set j value to be j minus 1, and the j plus 1 element with the value at temp, and print that the intermediate stage during the loop. Now I'm giving the list value and assign to the variable or the list variable end list, printing that before the sort, printing the list after the sort. Let's run it and see how it works. Here's the output of the program. The original list as hard coded, number of elements 6, and here's the sort process. So 23 and 1 happens to be smaller, should be coming to the left, it's getting swapped, and 10 is identified to be between, or the position happens to be between 1 and 23, it's placed there, and 5 between 1 and 10, minus 9, its position, I mean, since it's smaller, position should be at the beginning, so it's taken to the beginning, and 2 after 1 and before 5. So this is the sorted output list. Next we'll see about time complexity of algorithm. So we have seen three different sorting methods, right? Each has its own process, its own number of passes, and depending on the size of the data set, each is going to take its own time. So time complexity is nothing but the amount of time taken by an algorithm to process a set of data. In real world, the sorting algorithms are required to process huge amounts of data, right? I mean, and in samples we are seeing some 5 elements or 6 elements, max 10 elements probably, but they don't mean much in computer world, because with the CPU power and the application requirements, we are not going to come across this small sample data, right? And the systems that we come across, the social media systems or the data science systems, have huge amounts of data, right? So for dealing with them and sorting those, we need to have an idea about how much time each algorithm is going to take and what will be the best suited algorithm for certain type of data, whether sorted or unsorted, right? So these algorithms are required to process vast amount of data, and the total time taken will be significant factor in efficiency tracking. The aim of finding out time complexity of an algorithm is to study its behavior in case of order of input elements or size of data set. See, the same thing I explained earlier. For a given size of data elements or the order, whether it is sorted or unsorted, how each algorithm behaves, right? So the time complexity will be a good measure to identify what is the best suited algorithm for a specific application need. These are some basics to estimate time complexity of an algorithm. Let's look at some of them. Algorithms not having a loop can be considered to have a time complexity of 1. So you have a set of instructions, but there is no loop. They're executed just once, and those instructions are constant. It will not change between data sets. Given a program, given a set of statements, for each data set, these instructions are run and just once. So these are called constant time algorithms, regardless of the data size. Whether it is small data set or large data sets, these instructions will run only once because there is no looping. Algorithm with a loop of size 1 to n have a time complexity of n, because these set of instructions will be run n number of times, 1 to n number of times. It can break out in between, or all n iterations or passes will be going through, depending on the programming logic. It will run from a minimum of 1 and maximum of n number of times when there is a number of loops 1 to n or n. So these are called linear time algorithms. And algorithms having loop within a loop, or otherwise called nested loop, have a time complexity of n square, meaning if you have n as the loop and you have n within, so it will be running n square times. So these are called quadratic time algorithms. If an algorithm has a nested loop and a single loop, the time complexity will be based on the nested loop only. Natural, right? When a particular program or algorithm has a single loop and another place it has a nested loop in the same algorithm, we cannot go with the single loop and say the time complexity is just 1 or n, right? So depending on the nested loop, it's going to be n square or some other factor. So let's have a quick recap of sorting. The process of arranging a collection of elements into a particular order is called sorting. Bubble sort is the simplest sorting algorithm that works by repeatedly swapping adjacent elements in case they are unordered in n-1 passes. In selection sort, the smallest element from the unsorted array is swapped with the leftmost element, and that becomes part of a sorted array. The process continues from the next element in the unsorted array till the list is fully sorted. Insertion sort places the element of list at its suitable place in each pass. It is similar to placing of cards at its right position while playing cards. Complexity analysis performed to explain how an algorithm will perform when input grows larger or in a particular order. Let's look at some program expectations or programming samples that you can try hands on with. Write a program to sort alphabets in a descending order using all three sorting methods discussed. Write a program to receive a list of 10 integers from user and sort them in both ascending and descending order with insertion sort, showing the list at the end of each pass. Try the above with both bubble sort and selection sort also, and try some of them by yourself from your textbook or any other place, any other reference you might have. Try out a few yourself. See you in the next session. Thank you.